Okay, so now let's turn our attention to conservation of momentum. And here, if you remember from integral analysis, we started with Newton's second law for a finite system. So if we think back to that derivation, here we started with the idea that all the forces on a system are equal to the change over time in linear momentum of the system. Okay, so, and then also here, our linear momentum P is given as the integral over the mass of our system of the velocity dm. Okay, so this should look pretty familiar. This is what we used exactly before. And then here we can write this expression in terms of an infinitesimal mass dm. So we would say for an infinitesimal mass, we can rewrite this as dF, so an infinitesimal force associated with our mass, is equal to dm dv dt, again, of our system. Okay, so if you remember way back to the beginning of class, we talked for a moment about Lagrangian descriptions of motion versus Eulerian. We're doing fluid mechanics here, so Eulerian makes much more sense than Lagrangian. It's very difficult to track individual particles for a fluid flow, particularly if that flow is going to get complicated. So we'll note that this is the Lagrangian description of Newton's second law. So this is the Lagrangian description. And if we want to shift this into an Eulerian description, which is what is really going to be useful for us in looking at fluid flows, then we need to be really careful with what this time derivative does. So if you remember back to the beginning of class, we talked about what does the acceleration of a fluid flow look like? And it's really tempting to write that it's just dv dt, because that's what we're used to from physics, from dynamics. But for fluid flow, we can't really quite do that. And the reason is most easily illustrated with looking at a nozzle. So if you have steady flow through a nozzle like this, where this is your velocity, so it's steady, right? It's not changing in time. So if we just took a time derivative of this velocity flow, we would say the acceleration is 0, right? But we know that nozzles have a faster velocity at the exit than the inlet, right? And we know from conservation of mass that this has to be true. Otherwise, matter would be created or destroyed somewhere in this nozzle. Okay, so because of this reason, we can't just use a straight time derivative, and we need a material derivative that's denoted with capital D's. Okay, so if I rephrase this in terms of an Eulerian system, I would write that dF is equal to dm material derivative of the velocity with respect to time. Okay, and just to jog your memory, this is defined as follows. We have our velocity dotted with the gradient of the quantity that we're taking the material derivative. Here it's just velocity again. And then we have our time derivative part. Okay, so just to remind you, this is the unsteady part of the derivative, and then this is the convective part. So this is the part of the acceleration that is arising because of fluid particles being convected along with a surrounding flow field. Okay? All right, so if I expand this out, we have dm u partial v partial x plus v partial v partial y plus w partial v partial z plus dv dt. All right. Okay, so the right-hand side is pretty much well settled here. We have our right-hand side in terms of velocity and derivatives with respect to position. And then we also have this dm here, which we know we can relate also to differentials in terms of space through the density. So we know that rho is equal to dm over dv. So this dm we can rewrite as rho dx dy dz. So just keep that in the back of your mind. It's going to show up later when we bring everything together. But at this point in time, we really need to address what are these differential forces acting on our little infinitesimal value. All right, so now we want to take a look at that force term. So we're going to take a look at this differential force term. Okay, so if we take a look at our little infinitesimal cube here that we've drawn a couple times now, this is going to get really messy if I were to draw all the forces on it in just kind of a very arbitrary sense. So I'm going to first just use the x direction to illustrate what's going on here. So if you remember when we talked about stresses in fluids, we have normal forces that act perpendicular to all the faces, and then we have shear stresses that act tangentially. So if we take a look at, for this cube, what we have in the x direction in terms of forces. So here I'm going to just quickly draw our little coordinate axis here just so that we don't get lost in notation. All right, so the first one that we'll have is our normal stress in the x direction here. And then we'll have the same thing on this face, but here it's going to be the normal stress minus, you know what, I forgot a part of here. So all of our stresses, all of our forces act at our center point again. Oh, so if we want to know them on the faces, we have to do the same thing with the Taylor series expansion. So here our normal stress is sigma xx plus partial sigma xx partial x dx over 2. And then the same thing over here, we've got partial sigma xx dx and then dx over 2. Okay, and then we also have forces that are going to act in this horizontal direction on the front and back faces and the top and bottom faces, and these are going to be shear stresses. So I'm going to do my best to draw this here, a 3D thing in 2D. So the first one I'm going to draw is right here. This stress is going to be acting on the front face. So this one is given by tau zx. So if you remember our nomenclature here for shear stresses is that our first index is the plane on which it's acting, and then the second index is the direction in which it's acting. So this one is acting on the z face in the x direction. And so we have this quantity plus the differential with respect to z, dz over 2. And then similarly, we're going to have the same thing on the back face. So here we have tau zx plus tau zx divided by, or with respect to z. I'm sorry, this is a minus here because we're on the back face. And this would be dz over 2. Okay, great. So now we also have our top and our bottom faces to contend with. I'll start with the top one here. So it's going to go this way. And let's see where I can write this. Okay, so this one is going to be tau. We're acting on the y face in the x direction plus partial tau yx partial y dy over 2. And then the same thing on this bottom face. We've got tau y x minus tau y x, the differential with respect to y, dy over 2. Okay, so in the x direction, we have 2 normal stresses, and then we have 4 shear stresses. Okay, so we want to know what the sum of all of the forces in this direction are. So we want to know dFs in the x direction. And actually, we want to know all of dF, right? So we have dFs in the x direction, and then we're going to have dFs in the y direction and dFs in the z direction, right? So when I add all of these terms up, this is what I end up with. So for in the x direction, I have, make this abundantly clear where I'm working, dFs in the x direction is, we've got our sigma xx plus partial of sigma xx dx times dx over 2. And of course we have, this is a stress and we want a force, so we need to multiply by the area. So we've got dy dz, yeah? And then we're gonna have minus sigma xx minus partial sigma xx dx, and then dx over 2, again by the area. All right, so these are our normal stresses. Now we're going to do our 2 pairs of shear stresses. So we have tau yx plus partial tau yx partial y dy over 2 dx dz minus tau yx minus tau yx dy over 2 dx dz. And then for our last set of forces in the z direction, we have plus tau zx plus d tau zx dz dz over 2. Here the area would be dx dy, and then minus tau zx minus tau zx partial z dz over 2 dx dy. Okay, and when we look at this, again, like how we saw before with conservation of mass, we get a lot of things to conveniently cancel out. So just looking at this, we have our sigma x's cancel out here. Same thing with our taus in yx and zx. Okay, and so we can write this down in a much simpler fashion. Okay, so noting that all those terms, many of those terms cancel out, right? So we can write that dfs in the x direction is given as we've got partial of sigma xx with respect to x plus partial of tau yx partial y plus partial tau zx with respect to z. And then our volume is, of course, dx, dy, dz. Okay, so it's also worth noting here that we oftentimes look at the body force as well. So our forces is the sum of the surface forces and the body forces. You'll remember this from integral analysis. The body forces are considerably easier in terms of this derivation. So the body force in the x direction is just simply rho times gravity in the x direction, dx, dy, dz. And just to make this abundantly clear here, our rho times our volume, that's just the same thing as dm. So this is just g of x times dm, right? So mass times gravity. Okay. So extending from this, we have kind of a similar thing happen in the y and the z direction. So I'm not going to write it out in that kind of detail. I'll just write down this form for the y and the z directions. Okay. So this is all well and good. But if you remember back several lectures ago, we can actually write our stresses, so these taus and these sigmas, in terms of the velocities. So we're looking for a differential equation that is in terms of velocities. So that's what we're going to want to do. So just quickly to note here, recall that we can write stresses in terms of the velocity. And then of course, it's also important to note here that the stress tensor is itself symmetric. Okay, and that's important because that means that we can say that tau xy is the exact same thing as tau yx. So the index here, the x and y and x, it means the exact same thing. And that'll become a little more abundantly clear when I write the definition. So, so by this, I mean tau xy equals tau yx, which is equal to the viscosity mu times partial v with respect to x plus partial u with respect to y. Okay, so whether you switch these two differentials, they're additive, right? So it's the same. Okay, great. It is also worth noting, carve out some space for me here, that our normal stresses, we're also going to bundle in the pressure force to those terms. So if you'll recall, our normal stresses are acting normal to each of the control surfaces. And so that's the same direction that pressure acts as a force as well. So here we'll write that sigma xx, so this is a normal force, is going to be equal to the negative pressure minus 2/3 viscosity, the divergence of the velocity plus 2 times the viscosity du dx. Okay, great. And here I just want to note that P is the thermodynamic pressure. So this is the pressure that depends on density and temperature, and it's defined by what's called an equation of state. So an equation of state that you're probably familiar with would be the ideal gas law, for example. So P is a function of density and temperature, and it depends on the equation of state. Oftentimes abbreviated EOS. Okay, so now we want to combine our left-hand side with our right-hand side for the momentum equation. So if you remember, what we were looking at was dF is equal to dP dt, right? So we've got our time rate of change of our linear momentum and then our differential force. Okay, so we have, I'm going to write this in each of the directions. So starting with the x direction, we have that dm, material derivative of the u component of velocity, so capital D dt. So this is our, our left-hand side is equal to rho gx minus the gradient in the x direction with respect to pressure plus partial x of mu 2 du dx minus 2/3 the divergence of the velocity plus du dy of viscosity du dy plus dv dx plus the gradient with respect to z mu du dz plus dw dx. And then this, of course, is all still multiplied by the volume, dx, dy, dz. And if you remember a little bit earlier, I said that dm is just equal to rho times dv, right? And dv is just dx, dy, dz, right? So we can cancel this out, and then we would just have a rho over here. And that's what I'm going to do for the y and the z components, just to be perfectly clear. Okay, so this is the x direction. And then our y direction is then given as rho, so I'm making that substitution now, dv dt, and that's equal to rho g, the y component of gravity, minus the partial derivative of pressure with respect to y plus the partial derivative with respect to y of mu times du dy plus dv dx plus d dy mu 2 times dv dy minus 2/3 divergence of velocity plus partial derivative with respect to z mu partial v partial z plus partial w partial y. And then finally in the z direction, we have rho material derivative of the w component of velocity is equal to rho gravity in the z direction minus the partial derivative of the pressure with respect to the z direction plus partial derivative with respect to z of viscosity times partial w partial x plus partial u partial z plus partial y. I apologize, this should be x and this should also be x. Okay, partial y of mu dv dz plus dw dy. And then the last term here is partial z mu 2 times partial w with respect to z minus 2/3 the divergence of the velocity. Okay, and so these are what are called the Navier-Stokes equations. It's a differential representation of the conservation of momentum. And you can probably appreciate that these equations are pretty complicated, right? There's a lot going on here. There's partial derivatives with respect to all 3 directions. There's a derivative with respect to time. There's a forcing term here. And so these are really tough to solve, but they can get a lot simpler, especially if we consider an incompressible flow, which means that our density, again, is constant. And then if we also consider a constant viscosity, which is also a pretty fair assumption that your viscosity isn't drastically changing over a problem of interest, then we can simplify this quite a bit more. So here we're looking at this viscosity coming out of these derivatives. And I'm going to write that now. Okay, so as I kind of already alluded to, the Navier-Stokes equations for incompressible flow with also constant viscosity. All right, so this set of equations, we have a partial differential equation in all 3 directions, and they are given as follows. In the x direction, we have the density times our material derivative, which I'm going to write out completely here. And that is equal to our body force in the x direction. We've got our pressure contribution to the surface forces and then our viscous forces. So our surface stresses due to viscosity. All right, well, you're going to notice here before we had a derivative on the outside and then a whole bunch of derivatives on the inside. But since we can bring our viscosity outside of the derivative, now we have second derivatives in here. This is what's known as the Laplacian, sometimes denoted as this in vector format, just so anybody knows. Okay, so to write these in the y and the z direction then, we've got our material derivative again. Our body force in the y direction, our pressure contribution, and then we're going to have our viscous force again as well. And then same thing in the z direction. We've got our material derivative. And then our body force in the z direction, our contribution from pressure, and then our viscous forces. And those are probably the most standard form of the Navier-Stokes equations.